Hello, my name is Vanessa Guzman, and today we're going to learn how to graph rational functions. So, what is a rational function? A rational function is a function in the form of a ratio of two polynomials in which the denominator is not zero. Here we see that all the examples simply have two expressions on each side of the ratio. Rational functions follow the basic equation of f of x is equal to p of x over q of x, where both p of x and q of x are polynomials and q of x can never equal 0. The equation f of x is equal to x squared over x squared minus 25 shows that p of x is x squared and x squared minus 25 is q of x. Knowing this, when the value of x is 5, which will zero the denominator, the function output becomes undefined. Since the function is written as a ratio of two polynomials, these graphs will have hypothetical positions it may just approach. All at least have one of these positions, referred to as an isotope. Having a fraction made of polynomials too is unique, but the most distinct trait that makes it easy to point out a rational function is its incorporation of isotopes. These isotopes shape rational functions into the iconic graphs we see online. We will further discuss isotopes in the next slide. An isotope is an infinite line which marks the position where the curve will hypothetically approach. Isotopes will come in different types such as vertical, horizontal, and slant. Remember the word approach. The curve being affected by an isotope will never reach the isotope's value until the change in value reaches infinity. Thus the curve will only approach this infinite line. So let's learn what vertical isotopes are and how to find them. We need vertical isotopes whenever the divisor equals 0 for some value of x. We could easily identify vertical isotopes from making the polynomial in the denominator equal to 0. Before this, we must always stay aware that that polynomial is simplified and can be equal to 0. When the denominator is simplified and equal to 0, all the x values become vertical isotopes for the graph. But when we cannot have the denominator equal to 0, the rational function has no vertical isotope. Instead, it will either have a slant isotope or a horizontal isotope. Moving on to slant isotopes, we could simply put this process by simply putting it as if the numerator's degree is 1 degree greater than the denominator's, there is a slant isotope. We could find the formula by dividing the numerator by the denominator through either synthetic division or long division. Continuing, let's learn what are horizontal isotopes and how to find them. We sometimes have horizontal isotopes when our x value increases, but the denominator increases very fast and passes the numerator in extreme amounts. We should know the equation fx equals ax to the power of n, continuing, over bx m, continuing. This equation represents basic rational functions. N represents the numerator's largest exponent in the numerator's polynomial. Meanwhile, m represents the denominator's largest exponent in its polynomial. A and b are the coefficient of each variable who have the largest exponents. According to the differences between the two exponents, there are different horizontal isotope cases. When n is greater than m, the horizontal isotope is y equals 0. When both n and m are equal to each other, the horizontal isotope is y equals a over b. Lastly, when n is less than m, the rational function will have no horizontal isotope. Now let's go on with our problem. Let's first find all the isotopes of this graph. Here we see that the numerator's degree is not 1 greater than the denominator's. Instead, we see that this rational function falls into case 2 for a horizontal isotope. N is equal to m, which means that our horizontal isotope will equal to y equals a over b, or simply y is equal to negative 2 over 1. This means that as x forever increases, no matter the direction, so x goes to infinity, y will approach -2. Now let's graph the horizontal isotope. It'd be located at y equals -2. So right here. Label the axes. So the curve will always get closer to this line, but never be able to touch it. Now, let's attempt to find the vertical isotopes. We want to set the denominator equal to 0 in order to do this. So let's simplify the bottom. The bottom polynomial is a difference of squares, meaning that x squared minus 9 can be simplified into x minus 3 times x plus 3. When we set that equal to 0, we know that the x values are x is equal to 3 and -3. These are vertical isotopes. Let's graph them. So when x is equal to 3, the vertical isotope will be located here. And when x is equal to -3, the vertical isotope will be here. Now, let's try to find where our curves should be. In order to find the curves, we should see what happens as x approaches to one of our isotopes, approaching from one side. Let's start with x is equal to -3. So we want to know what happens as x approaches to -3 from the left side, so we could find out what happens to y. We could do this by using values on the left side of -3, which approaches this line. Values like that are -3.1. So if we input -3.1 into our equation, we will get y is equal to -31.5. Now let's continue one more time, and let's get even closer. So let's use the number -3.01 squared. Remember to use a calculator to make this easier. And when getting closer to -3 from the left direction, we got an increase to -301.5. So from these two samples, we could see that as x approaches -3 from the left direction, y actually approaches -infinity. Now what this means is that our curve will actually be located right here. This is because as x approaches -3, y approaches -infinity, which is what this arrow is doing. It also shows that as x approaches infinity, y is trying to approach -2, which is what this arrow is doing. Now let's continue and do the same for x equals 3. We will be approaching this value from the right side. So we shall input the value of x as 3.1 squared over 3.1 squared minus 9. That will also get us -31.5. Now let's get even closer. Let's use -2 times 3.01 squared over 3.01 squared minus 9. Now in the calculator, that tells us that is also -301.5. This also shows that as x approaches 3 from the right direction, y also approaches -infinity. This means that our curve will be located right here. Like the last one, as this arrow approaches 3, our isotope, y approaches -infinity. This arrow shows as y approaches -2, x approaches positive infinity. Now, let's repeat this process for our curve in between our two isotopes. We want to find values that are approaching -3 from the right direction. We're going to use the value -2.9 to see what happens. When our x is -2.9, we know that our y will become 28.5. Now let's get even closer. To get closer to -3 from the right direction, let's increase this to 2.99 squared over -2.99 squared minus 9. This will get us 298.5. Now what this shows is that as x approaches -3 from the right direction, y actually approaches infinity. Now this is quite interesting. Let's repeat the process, but for our other isotope, x is equal to 3. For this isotope, we will approach 3 from the left direction, meaning that our x value should be 2.9. By plugging this into the equation, our calculator gives us that by having x equal 2.9, y is 28.5. Now let's get even closer. Let's use the number 2.99 as x. This will give us y is equal to 298.5. This also shows that as x approaches to -3, y is still approaching positive infinity. So this curve would look like this. So as x approaches -3 and 3, y approaches positive infinity. So our rational function should have this shape. Of course, we could always just find rational functions by plugging in points and finding the shape through that, but this method also works. So this is our rational function.